Good afternoon, guys, gals, non-binary pals. It's nice to be here with you. My name is Kyle Kingsbury. You might know me as Afer from the internet, and I seem to be cursed with some sort of field which causes transaction systems, bureaucracies, car parks, even my fridge to suffer concurrency bugs. I've done the best that I can with the situation by writing a library to cause even more bugs. This is called Jepsen, and it's a way to test distributed systems. In Jepsen, we combine four major ideas, which I think will be familiar to many of you. First, it's a generative testing system, also known as fuzzing, also known as property-based testing. We invent random test cases, apply them to the system, and then check that some property holds. Why? Because distributed systems do lots of things, and it's difficult to write all those things down by hand. Second, it's an opaque box testing system. So we don't have any formal model of the system. We perform no source code analysis. There's no instrumentation, no proofs. All of these are great and complete parts of a balanced breakfast of testing. But in this particular case, I want to run real binaries, maybe from strangers who don't like me. And I'd like to run them on real computers, the way God herself intended, connected by an IP network. So this is a nice way to test that. Third, we do fault injection because real distributed systems are characterized by recurrent partial faults. So we need to do those faults to actually see what happens. Finally, it's a concurrent testing system, and this is important because distributed systems are fundamentally concurrent. Therefore, a test needs to do different things at the same time, and any of our generative properties need to understand that concurrency structure. Jepsen consists of a human operator who sits at their computer, the control node, and they run a little JVM program written in the Clojure Lisp-ish programming language. That program includes the Jepsen test library, and it opens up SSH connections to a bunch of machines. Those machines, the database machines, run the system under test. We use those SSH connections to set up a fresh cluster. We connect them over the network. And then we start a bunch of clients which can make requests to those systems and get responses. And together with the network and the clients, they should behave sort of like a coherent database or a queue or whatever you're testing. Now, while this is going on, we use those same SSH connections to inject faults. We can use IP tables to kill the network, TC to pause or drop packets. We can kill processes, pause them, jump the clock backward and forward in time really fast. We can cause the file system to pretend to lose data that wasn't F-synced, corrupt files, all kinds of fun stuff. Logically speaking, the fun stuff to do, the operations we want to perform and the faults, come from a thing called a generator. Big surprise for generative testing. The generator is a gradually unfurling data structure which responds to changing conditions in the test, and it says, next I'd like to read the value of object X, or next I'd like to add something to a list. And then I'd like to kill DB1, and let's set Y to 3. It invents things to do. You take one of those desired abstract things you want to do, and you put it into an append-only log called the history. Then you hand it off to a client whose job it is to actually execute that operation. The client turns it into, say, an SQL statement and sends it to a server, gets back a response, and produces an abstract completion operation, which will go into the history again. Those completion operations signify the end of the operation logically, and they can be of one of three forms. They could complete successfully, they could fail and we know they did not happen, or they could do something else, time out, crash, you don't know. In this case, we log an informational message and we leave the invocation open for all time because, just like in real systems, it might happen next Tuesday. Now this is going on concurrently. The nemesis, which does fault injection, and all of the clients are making requests, getting responses, putting things in the log, and we build up this concurrent data structure that shows us what the system did over time at an abstract representation. And then with that representation, we can ask questions like, was this history consistent with repeatable read? Now, repeatable read checking is somewhat involved. I have a whole talk on that. But to give you a short example, if I could find a write of x equals 5 that failed, and I could find a read of x equals 5 that succeeded, and there was no other write of x equals 5, I would know that I had a case of G1A aborted read. This is a violation of read committed, and also repeatable read, and serializable, and so on. So I look for these patterns in the history automatically, and that tells me the system's safe. Now I'd like to tell you about some of the research findings from the last year of work with Jepsen, starting off with MySQL version 8.0.34. MySQL needs no introduction. It is the workhorse online transactional processing relational database of our time. It has multiple replication architectures, all of which I will ignore. It has multiple isolation levels from read uncommitted to serializable. But for our purposes, I'm interested in repeatable read, which is the default isolation level. Now, repeatable read in the documentation claims that all consistent reads, and by the way, a MySQL consistent read is what happens if you do a select. This is a plain old select statement. All consistent reads within the same transaction read the snapshot established by the first such read in that transaction. Great, so I should read the same thing if I keep reading over and over again. That sounds like repeatable read. Let's go ahead and try it. So I'm going to make transactions that append things to lists on a single node MySQL system. And I will identify those lists by primary key. Those keys will have a corresponding value column, which is just a text field that's got some numbers separated by commas. We append using SQL concat. This is like bog standard SQL. And you can find transactions like the following. Transaction 1 and transaction 2 both read X and observe nothing. There's no value there. Each one of them appends something to key X. Transaction 1 appends 1, transaction 2 appends 2. If we have a read of X1, then we know that transaction 1's write to X happened before transaction 2's. But either way, the existence of this read-write cycle between them implies that we've violated snapshot isolation and onto repeatable read. We have a lost update. One of their writes must have been thrown away. And that's troubling because repeatable read, at least in the formalisms, is not supposed to do this. But it happens all the time in MySQL. And this is not news. This is actually something that Kleppmann reported in Hermitage all the way back in 2015. But I think it's worth emphasizing that it still happens because people don't understand that. And there's some degree of gaslighting about this. If you mention this to MySQL people, they'll say, you didn't do select for update. That, using explicit locking, is what makes it safe. No, that's not how the spec works. It's supposed to be safe regardless. Please get your shit together. Being somewhat aggressive here. But even if it were just that behavior, there's more. It turns out that you can have non-repeatable reads too. For example, if I select someone's name, it might be Pebble. And then I could change that person's name to, change that person's gender field to femme. And if I select their name again, I could see their name has changed to Moss, even though I didn't change it. This is P2 from the ANSI SQL standard, which is not an ANSI standard. It's also a violation of internal consistency. This is not a repeatable read. Somebody else's write just showed up in the middle of my transaction for no reason. Huh. Well, maybe MySQL repeatable read is actually monotonic atomic view, Sister Mary Holywater remarks. Let's try that instead. So let's make a table with exactly 2 rows, X and Y. Each one of them has a 0 value and a 0 no-op field. Why a no-op field? Because it's writes that cause the snapshot thing to break. And we'll do a bunch of write transactions, which update X to increment the value, and they update Y to increment the value. So the values of X and Y go 0, 0, 1, 1, 2, 2, and so on. Concurrently with these transactions, you can run the following. We read X, and we see value 0. Then we do a no-op write to Y. We select Y, and we get 1. We've now seen an increment transaction. But if we go back and select X again, we'll still see 0. Huh. So which is it? Do I get to see the new value or the old value? Depends on what rows you're reading. Under monotonic atomic view, once you observe some of a transaction's effects, you should observe all of its effects. But that's not what happens in MySQL repeatable read, or MariaDB for that matter. So in conclusion, MySQL and MariaDB, as of those versions last year, the repeatable read default allowed lost update, which messes up ORMs that do read, modify, write, unless they use explicit locking. It makes reads not repeatable. Reads are not even monotonic, and claims about snapshot reads are wrong. But there's good news. MariaDB and the lovely folks over there have written a new flag called InnoDB snapshot isolation, which makes repeatable read work like snapshot isolation. By the way, this is also what Postgres does. This fixes the non-repeatable and non-monotonic reads, and is now the default in MariaDB 11.6.2. So hooray. I don't know if it's made its way to MySQL. I haven't found it in those docs yet. If anybody hears from those teams, give it a shot. Second database, Datomic, version 1.0.7075. We have some nerds in the house. As an avowed closurist myself, I am really excited about Datomic. It's a distributed, serializable OLTP database for weirdos, and I And it offers temporal storage, so you can look back at the state of the database at any historical point in time. It's mostly immutable, modulo, say, redactions, and it offers pluggable storage backends with a data log, graph, and ODM-style query API. There's so much cool stuff to say about Datomic, but I am pressed for time, so I'm just going to tell you a little bit about the architecture. It involves peers, which are the applications. Those peers have a fat client that pulls down data from the storage system and runs queries locally to make them faster. When peers want to change state, they submit a transaction to a transactor, of which there's usually only one active at any given time. The transactors read and write to storage to produce new state, and that flows back to the peers. Logically, Datomic is like a giant spreadsheet with 4 columns. There's an entity, attribute, value, and time. If you know about RDF triples, this will look familiar, but temporal. This, for example, is a Datomic database with a single entity, number 1, whose name is NK Jepsen as of time 1, and whose Hue account was 2 as of time 2. And of course, there'd be previous states you could roll back to as well. The way that you modify this structure is by issuing a transaction request. And that's typically written as a vector of vectors. Each vector represents something you'd like to do in the transaction. Like, I want to add the fact that entity 4's name is Beyonce, and also add the fact that entity 4's alter ego is Sasha Fierce. But you can also call an arbitrary transaction function. Say I could drop album for Renaissance, and this calls a function called drop album, and it passes it the current state of the database, the artist for the album name Renaissance, and that function is expected to return new transaction data, which is recursively expanded until only adds or retracts remain. Now, the documentation at the time said that transaction functions, which can be arbitrary Clojure or Java or other JVM code, quote, can atomically analyze and transform values, quote, to ensure atomic read, modify, update processing and integrity constraints. So let's try an application with an integrity constraint and see if we can do atomic read, modify, update processing. I want to envision like approving a research grant, which starts off in the empty state, that's the fresh grant, and it can either be approved or denied, and we're only ever going to do one of those things to a grant. So you can never double approve, you can never approve or deny, approve and deny, you can never double deny, you can just do one of those things. To represent the approved state, I will put in a fact that the ID was approved at some time, and to represent a denied grant, I'll put in a fact that it was denied at some time. There should be at most one of these tuples. To write this down in code, I'll write an approve function, which takes the database and a given grant ID, and it will query the database to tell me, is there currently a record that says that this thing was approved or denied? If there is, I could throw an exception, which will abort the transaction. If it doesn't abort, I'll expand into the addition of a new fact that that particular ID was approved at the current date. This guarantees I never do multiple transitions for a single grant. The deny function looks identical, it just makes a denied fact. So we do a generative test. We produce randomized transactions that are, say, trying to approve the grant on one side and deny it on the other. Are any grants ever both approved and denied? That's a simple property. And it turns out, no. Datomic appears to be strong session serializable, which is actually stronger than its claimed property of serializability. That means that not only do transactions appear to execute in total order, but that order is consistent with the order observed by every single peer. So like, heck yeah, good job. It's actually strict serializable for writes. However, I'm so sorry. Imagine you're me, and in your foolishness, you write a transaction which tries to both approve and deny the same grant. Show of hands, who thinks this approves only? Who thinks this denies only? Who thinks this aborts? Who thinks it does both? We are a community of safety testers. You are right. This both approves and denies the grant. So how does this happen? Well, it starts off with the empty state db0, and then it approves with that empty state and says, well, is there an added or denied fact for 1, 2, 3? No. So I'm going to create an add fact for it. Great. Now I'll expand the deny function. I pass it the fresh db state with no approved or denied entries, and I can then deny it. And then we take the union of those two facts and put them into the database, and we get a database that has both approved and denied the grant. This is odd because what were safe transitions running in separate transactions have become unsafe transitions when we put them in the same transaction. That is the opposite of how most transaction systems work. Huh. So I, of course, stared at this in much more colorful language for a time. And the reason I got into this mess in the beginning was because it said, like, atomic read, modify, update. And transaction functions are serialized by design. And functions are called in turn. And these things are technically true. They are executed in strict order. But the semantics are not in order. Transaction functions, per the docs, are passed the value of the DB currently as of the beginning of the transaction, not the value reflecting other functions running in the transaction. And that's the key difference. This is actually by design. So most systems, when I say serializable, are, to make up a term, externally serializable. It appears that the effects of the transactions are equivalent to running them in a total order. And they're also internally serial in the sense that inside any transaction, they seem to do their steps one at a time. But Datomic is different. It's externally serializable, but the transaction functions internally all run concurrently. And this is just part of how the Datomic model is defined. Is this serializable? That's a really tough question. I wrestled with this for quite a while. Informally, yes, it's equivalent to a total order of transactions. That's how most people think about serializability. So I'm going to go with sure. But on another level, this doesn't match any of the formalisms that I know. As far back as 1979, Kung and Papadimitriou say that a transaction is a finite sequence of transaction steps. Thus, our transactions are straight-line programs. OK. Adjo Liskov and O'Neill, in their germinal paper on weak isolation, say that transactions indicate a total order in which they occur. And if you write something, you should later observe it in the same transaction. And the same is echoed in the abstract execution formalism and in the client-centric formalism. Like, all of the ways I know to define serializability say this is wrong. So maybe the formalisms are wrong. Maybe it's the youth. Or elders? I don't know. So maybe there should be a different formalism that describes these semantics. And after all, there are some nice properties to doing it this way. For instance, being able to read intermediate state in a transaction gives you weird effects. Like, maybe the state that I read doesn't actually come from any committed transaction at all. In Datomic, when you get a database state, you know that everything inside of it came from a specific transaction, and you can show where. That's kind of cool. Sort of. Yeah, OK. So Nubank says that this is unlikely to affect real users, and I think that's a plausible argument. They say that most of their transactions are simple. They don't do many transaction functions, and even if they did, there is a per entity attribute conflict checker which will detect if you produce a transaction that asserts two different values for the same entity and attribute. This only comes into effect when you assert incompatible values about different entity attribute tuples. In a way, this is kind of like snapshot isolation, but running inside a transaction as opposed to between transactions. And that's such a strange concept I have yet to wrap my head around. But it's neat. Finally, you could do an entity spec to constrain DB states. This is basically a predicate that runs on commit. But every transaction has to opt into running it. So I'm not sure that's necessarily a useful constraint unless you're careful. Bottom line, Datomic is not changing the behavior. This is documented. It's just confusing. And they've written much clearer documentation now. So I'm going to call it a win. Finally, last but not least, Buffstream version 0.10. Buffstream is a Kafka-compatible log service built for cloud deployments. It offers a number of data provenance features, including control of schemas. You can guarantee that all of the records written to your topic have some nice structure. Now, if you're not familiar with Kafka-style logs, basically they are a collection of named topics. I might have a topic for all of my grievances. And inside that grievance topic, because there's so many written per second, I divide it into what are called partitions. Karen DB. I divide it into partitions, and each partition is a totally order-dependent log. So when I put a record into a topic partition, it shows up at some monotonically, strictly increasing offset. And that offset tells me how far into the topic partition it is. Architecturally, Buffstream uses regular Kafka clients. They're wire compatible, so you just drop in your regular Kafka client and pull out. We use the Java client. It runs a number of stateless agents, which use a coordination service like etcd to communicate their state. And then it has an object store that it writes all the data to, for example, S3. Now, there's a couple of odd behaviors I found in Buffstream, which I've also seen in other Kafka-style systems before, like Red Panda and Kafka itself. And I want to just mention them because they're interesting. One of them is that transactions, even at read committed, allow writes to interleave. So if a transaction sends X and Y, some other transaction could sneak in and put a Z in the middle. If this happened in a traditional SQL system, I would probably call this G0. It's a write cycle, because the two wrote on top of each other. Writes aren't really atomic, at least not in the sense of isolation. They may be atomic in terms of all or nothing commit. So that's a little strange. That would be a violation of read uncommitted if it happened in an SQL database, but it might actually be sensible for a queuing system. Again, maybe we need new formalisms. Is this legal in Kafka? It depends on who you ask. Some of the Kafka documentation says this is illegal. Some of the Kafka documentation says this is OK. So OK. Another cool thing you might see is that you could send something to a topic, and then somebody else could write after you. But if you do a poll, you could see their write. And that's kind of circular information flow between you and some other transaction. This would be analogous to G1C, which is also a violation of read committed. Again, normal in Kafka, normal in Buffstream. It's supposed to be compatible, so it does the same stuff. In general, figuring out how to use Kafka transactions is a little tricky. There are many flags. The documentation is not at all straightforward. And instead of having sort of well-defined invariants or properties, it sort of gives you like a choose-your-own-adventure book where you get to glue together different features like fencing between zombie transactions and hopefully assemble the transaction semantics you want. The number of times I've written a correct Kafka transaction system is, after 8 months, 1. But this is actually, to some extent, it's doing Kafka dirty, because Kafka doesn't really want you to use transactions. You're supposed to use the Kafka stream system, which knows the blessed path to walk upon that does things safely. And I haven't tested streams at all, so that whole different ballgame there. We're down in the weeds in the internals of Kafka. All right. First thing we found in Buffstream, stuck consumers. You could have a queue that has A, B, C, D, E. You could poll A, B, C, and poll and poll and poll for an hour, and D and E would never show up. This was caused by 2 bugs. One of them involved, on restart, an agent returning stale or cached values for the last stable offset and the high watermark. And those are values that are critical to advance your readers. That was fixed in 013RC6. There was a second bug that caused the same problem involving etcd. Agents register a lease in etcd, and if their lease expired, they were supposed to be notified by a little callback mechanism, like a channel of updates in the Go program. But for some reason, the message about the lease expiry never showed up. And so they just assumed they still held the lease. They were still current, even though they weren't. That was fixed in 013RC8 by repeatedly polling etcd instead, or in addition to the lease. Second, we had issues with spurious 0 offsets. You could send a record X into a topic partition, and it would say, OK, I've got X. It's at offset 0, which is wrong. It's actually at offset 8, or 9,000. This occurred regularly with process pauses, crashes, or partitions. And it was caused by, of all things, a very sensible behavior on Buffstream's part. When Buffstream hit an internal timeout, it would hand back an error code to the client and say, hey, I got error 123. And the client, you would think, if it saw a non-zero error code, would assume that this message is an error. You would be wrong, because the Java client, the official one, only interprets it as an error if the offset field is -1. And they didn't set the offset field, because why would they? It's an error message. It has an error field in it. So this, to make matters weirder, their test didn't catch it because they were testing using Franz Go, which is the Go library, and it actually looks at the error code field, not the offset field. So as a result, different clients interpreted it differently, and this bug shows up in some clients but not others. Again, end-to-end testing. This is fixed in 013RC6. In 012, we also had frequent write loss in healthy clusters. And this is the most scary bug I found. Many as 240 out of 6,700 transactions could be lost in just 100 seconds. And this just happened all the time. Paradoxically enough, it was caused by a safety mechanism that they added to prevent write loss during transactions. Distributed systems are really hard. This was fixed in 013RC2. And I should note that Buffstream was in a sort of closed beta at the time. And so they were able to guarantee this actually never made its way out to customers. So no user-facing impact here. Finally, we had cases of aborted read. And this one was really flummoxing. Transaction 1 would send 424, 926, do a poll, send 927. And at the end of all of these operations, it aborted, which means that it shouldn't show up. And yet someone somewhere managed to poll 424, even at read committed. Huh. Well, what's even weirder is that 424 does show up, which is illegal, but 926 and 927 never show up, which is what you'd expect. So this one took a while to figure out. We had to dig deep into the packet capture traces, and we found out that before transaction 1, it executed transaction 0. The client sent some record over to N4, issued a commit message, and the commit timed out. OK. Well, it can retry the commit, so it does, and its retry succeeds. Great. Transaction 0 is now committed. It then goes on to do transaction 1. It sends 424, gets OK. Sends 926, OK. 927, OK. Abort, OK. This is a completely straight line, correct-looking transaction that should abort, except that the commit message shows up in the middle and ruins everything. Kafka sees the commit message and says, oh, I'm supposed to commit 424? You got it, boss. 927, that's a new transaction. So it tears the transaction in half. Some parts are lost, some parts are saved. Oof. And this is like a protocol bug, right? Like the commit and abort messages don't say what transaction they're committing or aborting. They just implicitly affect whatever transaction is in progress. There's an implicit assumption of ordering in the transaction protocol design, but the Kafka protocol is at its core unordered. It allows messages to flow to any server at any time from a single client. So there's no implicit order from the TCP connection. And even if there were a single server, it would reuse TCP connections, and that would introduce ordering problems too. So fundamentally, this is an unordered transport carrying something that assumes order. This is the end-to-end argument revisited. So the protocol has to add some sort of constraint to prevent it from allowing previous transaction messages to affect future ones. This allows aborted read, lost write, torn transactions. As far as I can tell, none of the guarantees claimed by Kafka actually held in these versions. And this didn't just affect Buffstream. It's a protocol bug. It shows up in Kafka, and I assume it shows up in other implementations as well. It might be masked by like timeouts or other timing sensitivities, but my guess is that it should be theoretically possible to hit everywhere. In short, the Kafka transaction protocol is broken at its core and needs to be redesigned. Not thoroughly, but there should be some sort of like ordering invariant or sequence number or transaction ID or something. There's an open bug for this now. It's Kafka 17754, which is still open, although I think some related bugs have recently been closed, so this may be fixed as of the release last week. Also, there are some mitigations possible. Clients can bump a certain sequence number that may be able to mask or prevent this issue entirely. In conclusion, databases are wild. The number of magical things you can get out of a database with very little effort is a constant source of delight for me. And even these simple tests, not stressing very much of the query engine, can yield surprising results. So I want to encourage all of you, and I don't think I have to because we're testers, but do some simple tests. Try end-to-end tests in particular. Not all of the time. You need to do unit tests, you need proofs, you need analysis, you need type systems. All of these things are helpful. But at some point, you want to verify that the client and maybe the etcd server and the libraries you're using to communicate in the network, those things impact correctness. If you isolate a component, you may prove it correct in isolation, but not see what it does in conjunction. So test end-to-end some of the time. Second, do fault injection. Because the easy path in distributed systems is the correct one, where all of the transactions flow as you expect. But when you start seeing timeouts and reorderings, that's when the interesting control flow comes into play. Third, do generative, property-based, fuzzing, DST, whatever you want to call it. Generate some randomized input, throw it at the system, validate that some predicate holds on those outputs. Even simple predicates can go a long way. Checking aborted read, for example, is not hard to do. Looking for multiple grants being approved is not particularly tricky to write. But you can get a lot of mileage out of them. If you want, try employing more sophisticated safety analyses. If you have a closed world, that is, you're the one generating all of the transactions, then you can do things like L, which is a checker I've been working on with Peter Alvaro. That does very general testing up to repeatable read or serializable. And it's the original finder of most of the bugs in this presentation. I wish I had more time, but we have to break here. So I want to conclude by saying thank you to Nubank, which funded the work on Datomic. They're the makers. And also to Buff Technologies, which makes Buffstream. And to my wonderful collaborators, my friend and mentor and co-author, Peter Alvaro, the team at the University of Portugal's Inestech, which wrote a file system fault injector for Jepsen, a whole bunch of folks there. Marco from the MySQL team, sorry, from the MariaDB team, pardon me. Artem Lifshitz and Justine Olshan from Kafka. Many people made this work possible, and it would not be here without their help. Thank you all for your time. If you'd like to learn more about this research, you'll find all the reports for free on jepsen.io.